Okay, we're about to discuss Charles's law. And Charles's law, as you can see right here, deals with temperature and volume at constant pressure. Similar to Boyle's law, which deals with pressure and volume at constant temperature, Charles's law deals with two variables, and the other variable is constant temperature and volume in Charles's law. And so that at this point, I would be asking you, okay, what's the relationship between temperature and volume of a gas? Because if you think about it, you already know if you have a bag of chips, you buy a bag of chips, and you're in uh, an air-conditioned grocery store, and there you go. This bag of chips is just the bag of chips, and you take it out, put it in your car, put it on the dashboard, for example, and it's warm. And a little while later, you notice that the bag of chips is full, like it's going to pop. And the reason is the temperature has increased and the particles of gas have started to go more quickly. And since they're moving more rapidly, they collide with the walls of the bag more often and with more force. And so they make the bag tight. So the volume of the bag increased when the temperature increased. Alternatively, if you were to put the bag into a freezer, it'd be kind of dumb to put a bag of chips in a freezer, but just for argument's sake, you go check on the bag of chips in a little while, and now the bag is all limp, and the volume of the bag has gone down. And the reason being, the temperature has gone down, and since the temperature has gone down, the speed of the gas particles has gone down, and now they're not running into the walls of the bag as often or with as much force, so the pressure went down. So as a result of that, the volume went down. So the temperature went down, the volume went down. The temperature goes up, the volume goes up, and a relationship like that where uh, as one variable increases, the other variable increases, or as one variable goes down, the other variable goes down, that is a relationship of uh, direct proportionality. So let's see. Temperature and volume are directly related. And that's it. That's all you have to say. If you start saying things like uh, as temperature goes up, volume goes up, and that's what you respond on a test, then the question I will ask is, what about when the temperature goes down? And I'll take points away. So you've got to have both arguments in there about temperature goes up, temperature goes down, volume goes down, unless, this is strange, unless you just say temperature and volume are directly related, and then it's all done. You don't have to say anything else. We've had that discussion before. So Charles's law states that temperature and volume of a gas at constant pressure are directly related. That's it. No mas. There we go. And I guess I can turn those off. All right. So stated mathematically. So what's the formula that deals with a direct relationship? Uh, if you remember Boyle's law deals with the inverse relationship of pressure and volume, which is P1 times V1 equals P2 times V2. And so this is a direct relationship, which is, of course, different than an inverse relationship. And the way these turn out, if I were there, we could figure it all out. But I'm not, so I'll just go with it. What you say is volume 1 divided by temperature 1, and don't underline that, by the volume 1 divided by temperature 1 is equal to volume 2 divided by temperature 2. And that's it. V1 over T1 equals V2 over T2. I'm going to put a little deal right down here that says temperature must be in kelvins. If the temperature is not in kelvins and you do whatever you do, it's wrong. And that's it. We're all done. Charles's law. There you go. So let's see. I wonder if I can now do this with a little writing stick. Oh, I don't think I can write on Word. Oh, I don't know how to do that. Crap-ola. Oh. Well, we'll see how this works out. So my little bookkeeping thing. Let's see, volume, and I'm not going to hit the subscript. Volume 1 equals 7.35 liters. Temperature 1 is 1.1 degrees C. And I'm not going to put the little degree sign up there because it takes too long. And I'm just going to go right ahead and say plus 273.15 equals, yikes, semicolon. That's better than an equal sign because then I got a whole herd of equal signs. So that would be 304.25 kelvins, right? 31 plus 273. 3 plus 1 is 4. Yes, I believe. Eek. Volume 2 is, we don't know. And temperature 2 is 8.5. And so I'm just going to add 273. So 8 and 5 is 13. 283.65 Kelvin. Yes. And then I'm going to solve that equation for V2, which would consist of multiplying both sides of the equation by T2. So I'm going to end up with T2 times V1 divided by, get back up there, get up there. Somebody's calling me, I don't want to talk to him. Divided by T1. Yikes, this is hard. I wish I could do this with a pencil. Equals V2. And then I'm just going to substitute all those values in right there, and we're going to be done. So T2 is 283.65 kelvins times V1 is 7.35 liters, and I'm going to divide that pile by T1, which is 304.25 kelvins, and the kelvins divide out and we're done. So I need a calculator. Yikes. And I also need the calculation. I don't know if I can do this. Maybe I can make that littler. Ha ha. 283.65 times 7.35 equals divided by 304.25 equals 6.85 to 3 sig figs, and we've got 5 sig figs, 5 sig figs, 3 sig figs. We are done. Bong is 6.85 liters. Oh, grr. Lose the underline and include an equal sign. Ha ha. And that would be V2, and we're done. So I'm going to make that bold and wonderful. This one, Charles's law, 33.2 liters of carbon dioxide at 25 degrees is heated. What must the temperature of the carbon dioxide be to be raised to if the volume of the carbon dioxide increases to 41.3 liters? Well, I don't know, but I know that V1 is equal to 33.2 liters, and boy, this would be a whole lot easier with a pencil. And T1 is 25 degrees C. And 25 plus 273 equals 298 Kelvin. And V2, what did we do? We expanded the container, made the container bigger. So that's 41.3 liters, and T2 is, we don't know. So I'm going to take that formula right there and solve it for T2. Oh, nice, Pace. We got to solve for the guy in the denominator. Oh, lovely. Wow. There's a whole bunch of ways to go about doing that. Solving proportions, and this is just a proportion. Students generally like proportions, by the way. To know what this variable is, if you do this with cross products, which is what most students do, they just take these two, v1 times t2, and set that equal to those two, t1 times v2. So v1 times t2, I'm going to write that down. v1 times t2 equals t1 times v2. Holy crap. v1 times t2 equals t1 times v2. And then I'm going to divide by v1 to get t2 by itself. So then t, nothing. So then t1 v2 divided by, I'm after t2, so t1 v2 divided by v1 equals t2. And then I'm going to plug those values in that equation right there. And by the way, most students, they plug these values right here in that equation right there, and then solve it with the numbers. Knock yourself out. I don't care. That's not what I do, but you know. Alrighty. So T1 is 298 Kelvin times V2, which is 41.3 liters. And I'm going to divide all that pile by V1, which is 33.2 liters. And then when you do all that, the liters divide out, and we're left with kelvins. And the kids will say, do you have to change it back to degrees C? Of course you have to change it back to degrees C. When was the last time you ever had degrees Kelvin reported to you that had any sort of meaning? Oh, this is 321 Kelvin. It's like, okay, is that hot? Is that cold? I don't even know. Man, this is a 4-alarm pain trying to do this in Word. So that's 298 times 41.3 divided by 33.2. That would be 370, yeah, 370.7. Kelvins to 3 sig figs right there. And then I'm going to subtract 273, and I'm only going to subtract 273 because I'm good to 3 sig figs anyway. And I'm not going to do that in my head. 370 minus 273 equals 97 degrees. Only this time I'm going to put the little yikes. Ah, I've got a degree sign in there somewhere. Where in the name of... Forget about it. Nope. Nope. Okay, there's a little degree goes right there, and then degree C. And then we're done. So when you... I'm going to bold that out. When you increase the temperature from 25 degrees C to 97 degrees C, the volume increases from 33.2 liters to 41.3 liters. So the O, I'm going to put equals T2. Ta-da, we're done.